Hi guys, today I'm going to cover the lesson about the quantum mechanics. And the title for today's note is going to be Light, Electrons, and the Quantum Theory, which is about the arrangement of electrons in atoms. Okay, so the background of the quantum mechanics started with a puzzle of the atom. Protons and electrons are attracted to each other because of the opposite charge. Yeah, we know that so far. Protons are positively charged and electrons are negatively charged. Electrically charged particles moving in a curved path give off the energy. So when the electrons they move around the central nucleus in a curved path, and then we have found out that whenever they are moving around, they are actually giving off a very small quantity of energy. And despite of these facts, atoms don't collapse. Somehow electrons are able to keep a certain distance away from the central atom. And every time electrons are moving from one pathway to another pathway, the energy changes. And these are the things that we could not explain. So we're gonna start off the whole idea of quantum mechanics with a wave-particle duality. First of all, there's a person called J.J. Thomson. He won the Nobel Prize for describing the electron as a particle. So, J.J. Thomson is the one who actually discovered the presence of electron. And when he discovered the electron, he described the electron as a little thing. It's a little particle. So he said the electron is a particle, and then he eventually won the Nobel Prize. And he has a brilliant son, and his name was George Thomson. He also actually won the Nobel Prize. But ironically, he won the Nobel Prize for denying his father's work and saying that the electron is not a particle, it's more like a wave it's a wave. It's not a real thing, so it is just a movement of certain matter. And then he said the electron is not a particle, it's just type of energy. It's an energy wave. Now, in the later times, there's another French chemist. His name was Louis de Broglie, and he's the one who said, well, the matter can behave like a wave. And he also supported George Thomson's idea that electron is a wave. And then he said, well, electron is going to move in a real space as an energy function. And he said that the electron is going to behave like an electromagnetic wave, which has a very specific set of behaviors. All right, so electromagnetic radiation. I know this already sounds super nerdy, but we have to first understand how electromagnetic radiations work. And electromagnetic radiation propagates, also meaning that just moving around, okay, moving through the space as a wave, moving at the speed of light. So, electromagnetic radiation is basically a wave moving at the speed of light, and it's going to have specific behaviors. First of all, you need to understand the components of the wave. Okay, the distance from the midline all the way to the peak of the wave is called amplitude, and the distance between the one peak to the next peak is called wavelengths, and number of wave in a given period of time, usually for 1 second, and the number of wave is called the frequency. And this can be actually mathematically put together, and this is the equation for that. Okay, the first of all, the c stands for the speed of light, and speed of light is constant. Okay, this will never change, and this is equivalent to 3.00 times 10 to the 8th power meter per second. The next one, this one looks like a V, but it's not a V. This is actually a Greek letter called nu. And nu is going to represent frequency. And frequency is in unit of hertz, or we sometimes actually call this one over second. Okay, hertz and 1/2 are the same thing. Lastly, this weird looking symbol is called a lambda, another Greek letter, and the lambda represents the wavelengths, and this is measured in meters. So the relationship every time when something is moving in electromagnetic radiation, okay, the speed of light is equivalent to the frequency multiplied by the wavelengths of that electromagnetic radiation. Okay, electromagnetic spectrum and the types of electromagnetic radiation. So, how are the electromagnetic radiation relevant to our life? Well, let's take a look at this. So, the types of electromagnetic radiation is listed by their energy and also the wavelengths in meters. Okay, so this number, 10 to the negative 12th power, means that it's going to be 1 over 10 to the 12th power meter. So that means it's extremely short, and all the way to the 10 to the 4th power, that basically means 10, 100,000. I'm sorry, 10,000. And then 10,000 meters, that's roughly about 6 miles or so. So this one's a pretty long wavelength. So the short wavelengths start with the gamma rays. The gamma rays are the one that has the highest energy in joules, and these are very destructive, and they're bad for human if you're exposed to that. And then the next one is the X-rays. We all know that the X-rays are used medically to take a picture of your bone, right? To find out if you have a fracture or cracked bone or broken bone. Because the X-rays are the electromagnetic radiation. They can penetrate through your flesh and skin, but not your bone. So this is used to take a picture of your internal body without cutting it open. But these are actually pretty bad for us, which is why whenever you take an X-ray, right, you're gonna be using the vest that's made up with the lead, because X-rays cannot penetrate the lead. So we use the lead vest to protect your body. Ultraviolet, which is also known as a UV, and this is going to be also the form of the energy transferred by the sunlight, which is why whenever you're going out there in a vacation on the hot sunny days, you are going to be putting the sunscreen, because these creams are known to deflect ultraviolet, which transfers the heat energy. So when you have a sunblock on your skin, the sun cannot transfer the energy to your skin because most of the energy is in ultraviolet and they get deflected. Now, this is going to be the visible light, and this is the only part of the electromagnetic radiation that's visible and detectable to our human eyes. So here's a color variation for that. And then we go to the infrared, and then infrared is the energy wave that we use to transfer information, such as like Blu-ray, Wi-Fi, remote controls, and all these signals that we use are going to be used by the infrared. And then we have microwaves to heat up the food, and radio waves. So we typically say that any kind of electromagnetic radiation with the wavelengths that are longer than visible light are safe, and that the shorter than wavelengths are the dangers to human. Okay. All right, let's move on to the quantum concept. The next guy I'm going to introduce is called Max Planck. Well, Max Planck is also known as the father of the quantum physics, because he's the guy who came up with the idea that matter can gain or lose energy only in small specific amounts called quanta. And this is the guy who came up with the whole idea about the quantum. The quantum is the minimum amount of energy that can be gained or lost by an atom. So he's basically the guy who tried to measure, okay, the smallest amount quantity of energy that can be ever transferred. So quantum, only certain values are allowed because they are the smallest quantity of energy that can be transferred. Okay, so far, we have many different ideas actually about into quantum mechanics. We have some guys saying that the electrons or electromagnetic radiation is a particle versus it's a wave, and we have the guy who developed the idea of how to measure and also apply the smallest amount of energy into calculation. Okay, so light as a wave and a particle. So what about light then? So we are exposed to light everywhere, and our eye, the detection, our vision basically works by the light, right? We are able to see the anything around us because of the light is being deflected and shows a color. So Albert Einstein, here comes a guy. He said he came up with an idea called the photoelectric effect. So photoelectric effect provides evidence for the wave-like and particles-like natures of the light. So Albert Einstein basically put George Thomson and J.J. Thomson's idea together. Said that some matter can be both. They can be both wave and a particle. So this is basically the idea he came up with it. So whenever light is traveling in an empty vacuum space, they're actually moving in a wave. So they're not a real thing. They're just energy movement. But the moment when the light strikes a surface of anything, any kind of matter, then what happens is that the wave is going to quickly bounce out a small particle called a photon. Okay, so it is a little particle now is generated by simply running into the surface, and the photon is given off. Okay, so light is a wave that carries with a tiny particles called the photons. So photon is a massless bundle of energy that carries a quantum of energy. So this genius is the one who basically tied everyone's idea together. So Albert Einstein said that sometimes, matter can be both particle and wave, right? Tying the J.J. Thomson and George Thomson's idea. And then whenever a photon is given off by a light running into surface, it's going to give off a certain energy, which was defined by Max Planck as a quantum. Okay, so he tied everything together into one theory, and that was called the photoelectric effect. And he also won the Nobel Prize for that. Okay, so this is basically the was going to be the lab experiment, but unfortunately we can't do that anymore. But this is basically whenever you are exposing pure element to the super high energy, and then each element is going to give off their specific energy level. That whenever they gain energy, they're going to reflect some of the energy back to us as in form of a light. So, for example, when hydrogen is given energy and gets excited, it gives off a certain color, such as here red strip, and here's light blue, here's blue and purple. These are the lights given off by the hydrogen. Every element has their own unique set of this color, and each color can be then converted into the energy level. So this is actually called the emission spectrum lab, and this is actually a pretty important lab for this physicist to or astrophysicist to analyze the light coming from outer space and then analyze the color to find out which elements are found in a distant planet. Okay, so you need to understand that long wavelengths, whenever the distance between one wave to the next wave is long, it means that there's a low frequency, and also that means low energy. On the other side, when wavelength is short, the frequency is high, and that means the energy is high. So the red one is the one with relatively long wavelengths and a low frequency. And the blue one down here is the one with the short wavelengths, therefore having a high frequency. Okay? and then a low frequency, low energy, high frequency, high energy. Okay, the energy of electromagnetic radiation is directly proportional to the frequency of the radiation. This can be also mathematically put together. Energy is equal to H times nu, while the E stands for the energy, which is usually measured in joules, and joules is the, or sometimes kilojoules, is the unit for the energy. H is called what we call them Planck's constant. Yes, this is the same guy we mentioned earlier today, Max Planck. And this is the guy who came up with the number 6.626 times 10 to the negative 34th power joule times a second. And the nu, again, we already learned that from other slide. This is for frequency, and frequency is measured in hertz, or also 1/second. All right, let's quickly review. Okay, qualitatively, a wave with a long wavelength has low frequency, and that also means you have a low energy. Qualitatively, a wave with a short wavelength has a high frequency, and also that means it has high energy. Okay, now let's go ahead and put all this information in equation together into math problems. Microwaves can be used to transmit information. What is the wavelength, which is a lambda, of a microwave having a frequency, nu, of 3.44 times 10 to the 9th power hertz? We are trying to calculate the wavelength, which is lambda. We are given the frequency, which is nu, and I'm going to go ahead and write them down. And we know that there are only two formulas, two math equations for the quantum mechanics we have learned so far, and these are these two. Speed of light is a lambda times nu, energy is Planck's constant times the nu. Based on these two equations, you should understand that speed of light c is given, it's always constant, and also as the Planck's constant h. Since you know the nu, right, and you know the speed of light, you have to be using the first equation to calculate the lambda. So I'm going to go ahead and choose this equation. I'm going to go ahead and rearrange the equation, okay? So lambda is equivalent to c over nu. Again, this is using the literal equation to basically rearrange the variables. This is equivalent to speed of light, that's constant, then that'll be given to you. Okay, you don't have to memorize it. 3.00 times 10 to the 8th power meter per second divided by the nu, which is given to us 3.44 times 10 to the 9th power 1/second, which is also the same thing as hertz. Now you divide these two numbers and we put into the three significant figures. Your answer is 0.0872 meters. Tiny water drops in the air disperse the white light of the sun into a rainbow. True. And what is the energy of a photon from a violet portion of the rainbow if it has a wavelength of 415 nm, which stands for nanometer, and the conversion is given to you. 1 meter is equivalent to 10 to the 9th power nanometers. So basically, I'm asking you how much energy does rainbow, the purple section, violet section, is giving off. Okay, so we are looking for the energy, right? How much energy is given off by the rainbow from the violet portion? We know that the wavelength is 450 nanometers, but since we're going to be using the meters, let me just first go ahead and convert this using the dimension analysis to use the conversion factor to calculate the meters. Okay, we need to use, we only know the two different math formulas. This time you know the lambda to calculate the energy. So it looks like the second equation is handy because this one is directly calculating the energy. Unfortunately, you are given the Planck's constant, which is a constant value. Again, you'll be given this value. You don't have to memorize it, and you have to know the frequency, which is nu. But unfortunately, you don't know the nu, right? You only know the lambda. So what I'm gonna do? I'm gonna first use the first equation to plug in the lambda into the formula and to calculate the nu. And once I get the nu, I'm going to then put it into the second formula to do that. So this question is a little bit more advanced because you have to use both formulas. All right, so I'm going to first go and rearrange my first equation to isolate the nu, which is going to be now speed of light over lambda. Speed of light is constant, and the lambda was calculated by the meters. Divide these two numbers, that will give me the frequency, which is going to be 7.23 times 10 to the 12th power, 1/2. Now I'm going to go ahead and plug this frequency into this second formula. Planck's constant is also given, it will never change, and then you multiply it by the frequency you calculated, and then reporting three significant figures, this is the answer we get.